we had originally in the 1970s, there was a kind of a first wave of AI successes, and we had some programs that were more like demos, but that actually showed some pretty strong, pretty impressive performance.
This is Boi Faltings, a full professor of the IC school at EPFL.
And at that time, the prevailing thinking was logic. So the operations were modeled by logic, by predicate logic, and we were talking about basically reasoning being logical inference, and the AI programs worked through logical inference.
So, roughly speaking, AI researchers used to believe that classical logic would be key to artificial intelligence.
Of course, you realize at some point that the world is not always true and false, but there's a lot of uncertainty in the world. So, in the 1980s, when we were more looking at real applications, so particularly expert systems, which were used quite broadly in the real world, and which I use to this day quite broadly, then it quickly became clear that things were not always true or false, but they were often true to some degree and false to some degree. And so in the 1990s, there was finally a good solution, which was Bayesian networks, causal reasoning with Bayesian networks, mainly pushed by Judea Pearl, who later got the Turing Award recently for that.
The Turing Award is often regarded as the Nobel Prize for computer science, since back when the Nobel Prize was created, computer science was not yet much of a science.
And that actually really transformed AI, because it allowed systems to get much bigger. Once you were liberated from this necessity of having always logical consistency, because logic with true and false, once you have a contradiction, you can infer anything. So there's no longer any truth or false in the system at all. So there was always difficult to build very large systems, because things do become inconsistent at some point. We know that when we write papers, we have to be very careful to keep everything consistent.
Plus, as all data scientists should be aware of, data is always messy and unreliable. So if you have a learning system that's too rigid, it's going to completely break down once you feed it with some corrupted data.
You are pushed towards dealing with uncertainty, to having actually things that are maybe true only some % of the time or to some degree. And so this was modeled, this was very difficult to model actually originally, because once you have probabilities and you have dependencies between events, it becomes very, very complex to build such models.
Here's why. Suppose you have 70 variables to work with, each of which is a binary variable that says, for instance, if an image contains some hand, some nose, or some head, or whatever. The problem with using probability theory to describe all of these variables is that you need to compute each possible combination of these variables. And there are a lot of possible combinations, 2 to the 70 as a matter of fact. And that's huge. That represents more than zettabytes of data. So you cannot use full probability theory for the data analysis of 70 variables, let alone to analyze images whose pixels require millions of variables to be described.
And Judea Pearl realized that when the model becomes causal, so that you actually understand things as A causing B, for example, and not B causing A, then you can find a more restricted graph of interdependencies that allows you to do reasoning with probabilities in a quite manageable way, quite manageable efficiency. And that created a huge wave of applications in expert systems first in the 1990s.
Such graphs of partial causality are called Bayesian networks or Bayesian nets, and crucially, they allow for Bayesian reasoning. But what's Bayesian reasoning?
So the difficulty is always that I gather information, maybe from sensors or from other sources, right? And then I want to make a certain decision about some outcome. So I'm interested in what is the conditional probability of this outcome, or of this outcome being a good one, let's say, given all this information that I have. And so in Bayesian reasoning, I actually say I will compute this based on a prior. So I have some prior expectation before I collect any other information. And then every piece of information that I collect allows me to update this belief. So I get a belief update in what is the probability of this event or of this variable taking a certain value. And so it allows me to integrate kind of gradually all this information that I'm gathering.
Now, Bayesian reasoning does not actually require a Bayesian net. However, Bayesian nets have been a major breakthrough to implement some sort of Bayesian reasoning.
The importance of causality in there is that when you have a structure in which the event you're trying to determine is a cause that manifests itself in different symptoms, you can treat each of these symptoms as being independent. So you don't need to know the correlations between those different symptoms. And that, for example, if you do diagnosis, so diagnosis of a disease, you have the disease as the unknown variable that you're trying to find out. And the symptoms, they all actually are caused by the disease. I mean, at least that's what we believe in a causal model, right? And so since they're all caused by this disease, you can treat each of the statistics between symptoms and disease independently. You can collect independently those statistics. You don't need to build one huge study where you have all combinations of symptoms and you link them to that disease, but every symptom can be linked individually. And the Bayesian reasoning tells you that you can combine these without knowing dependencies between them. And so that's the important role of causality. That allows you to do that. And before, people thought, wow, you need to build all this joint probability distributions, which are usually complex, and you could never find all the data to get them, and so on. So people had ruled out probabilistic reasoning for many years and thought that was just infeasible.
And importantly, now using Bayesian nets, you don't need to have an exhaustive description of all the probabilities of all the possible combinations of all of your variables. The Bayesian network structure restricts what these probabilities even can be, and thus serves as a sort of Occam's razor to promote simpler models.
In the beginning, people just wrote down probabilities themselves. So it was kind of a guess, you say, okay, there's about 40% or 70% and so on. And that worked pretty well, actually. It produced pretty good results.
Another crucial selling point of Bayesian reasoning in general and Bayesian networks in particular is that they are perfectly fit for machine learning.
And then afterwards, it all went to learning. So, clearly probabilities, you can just measure them. You can just look at samples from the real world. And so that opened up a lot of things, including these self-driving cars, but many other systems too, where you had an interface with the real world. You could actually get these, probabilities, and then you could link them together through Bayesian reasoning to get optimal decisions. And so that did a lot for building autonomous AI systems. Another area is the stock market. I mean, financial markets. Today, most stock trading is done by intelligent agents. Sometimes not very intelligent because they have to take decisions very quickly, but generally based on some probabilistic reasoning models.
These probabilities are related in the sense that if you found out that this person got into Harvard, that should increase the probabilities you put on both them having a high IQ and also them being a legacy.
With really artificial intelligence driving cars, we can actually build a much better system that coordinates traffic better, and that would all get us much faster to where we're going.